in many practical applications, you would see that you would like to prevent a surface from receiving radiation or a surface losing its energy through radiation. Let us take the first point, that you do not want a surface to receive energy by radiation. One of the practical examples where you encountered this situation is for cryogenic storage of liquids which are at a very high, which have a very low boiling point. Let's say you have liquefied air, or you have liquefied nitrogen, ammonia and so on, and you are storing them in containers. You try to insulate them as much as possible from the outside, but in order to reduce the radiation which is coming from the ambient to the tank which has stored liquid nitrogen, sometimes it is advisable to put a shield around the container. So, if you have a spherical container for storing liquid nitrogen, what you would do is these spheres are never, the walls are not solid. You may have on the inner sphere which holds the liquid nitrogen another layer of a material which surrounds the sphere, and this outside sphere, the outside covering of the main tank, they significantly reduce the radiative heat that comes to the sphere from the ambient and thereby heating up the liquid nitrogen inside. So, these kind of protective shields are known as radiation shields. So, in order to choose the material of construction for a radiation shield which is going to protect the inner core which you would like to keep at a lower temperature, that is very important. We need to know what should be the radiative property of the radiation shield. So, radiation shield is something which hinders the flow of heat through it, hinders the flow of radiative heat through this, thereby protecting the cooler temperature, the cold storage inside. And we are going to find out what is the property that needs to be, what is the property of the material of this radiation shields. One property is obvious, that means it should be opaque. That means the radiation, there is not going to be any transmission of incident radiation through the shield to the other side where you would like to keep the temperature cold. So, the first property of a radiation shield is that it must be opaque in nature. So, we take care of the surface property, that it is to be opaque, transmittivity should be 0. But what about the emissive property? Does it have to have a high emissivity or a low emissivity? Which one is going to be preferred for a radiation material? So, that is the one which we are going to study now. What would be the emissive property of the material that is to be used for radiation shield, and what kind of modification to the equation we need to have in order to incorporate the presence of radiation shield in a heat radiation problem. So, let us look at the case in which you have a surface over here which is the plate, which is a plate, I call it as plate 1, which is maintained at a temperature T1. Its property is epsilon 1, area is A, and then you place another one which is the radiation shield, and I call it as surface 3. So, the temperature is T3 on this side and T3 on the other side. Let us, for generalization's sake, assume that the emissivity of the material 3 radiation shield which is facing 1 is epsilon 3 and the emissivity of 3 which is facing 2 is epsilon 3 2, and this is, let us say, the plate 2, where the temperature over here is T2, the emissivity is epsilon 2 and the area is A. So, this is we are considering radiation heat transfer between two. So, we are considering radiative heat transfer between two very large opaque plates parallel to each other. And we put a radiation shield in between. So, this is more or less what we have in this. So, the heat flow from 1 to 2, therefore, Q 1 to 2 must be equal to whatever be the potential of this and whatever be the potential of plate 2 if they were black bodies. So, it is E B 1 minus E B 2 by the sum of all the resistances. So, what are the resistances? One is R 1, the second one is R 1 to 2 and the third one is R 2. So, if there is no radiation shield, let us first consider this and then we will consider the radiation shield in between 1 and 2. So, if there is no radiation shield in between 1 and 2, what you would get as Q 1 to 2 as sigma T 1 to the power 4 minus sigma T 2 to the power 4, and the first resistance. So, we do not have this anymore. So, the first resistance is going to be the surface resistance to radiation for surface 1, which would be 1 minus epsilon 1 by A 1 epsilon 1, and the third resistance is going to be the surface resistance of 2, which is 1 minus epsilon 2 by A 2 epsilon 2, and the right now we do not have this, we do not have the radiation shield. So, the radiative exchange between 1 and 2, the resistance for that would be 1 by F 1 F 1 2, 1 by A 1 F 1 2. Okay. These three are going to be the resistances, and for parallel plates A 1 would be equal to A 2, let us say this is equal to A, and of course, if the parallel plates are close to each other, in that case F 1 2 would be equal to 1. So, therefore, all energy emitted by 1 is going to strike 2 if these two are very close to each other. So, no energy will escape through this if they are very close to each other. So, F 1 2 is equal to 1. So, what you would get Q 1 to 2 would be equal to A sigma T 1 to the power 4 minus T 2 to the power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1, this is in watts. So, once you A1 A2 are same. So, I take the A on the numerator. So, the numerator becomes A times sigma T 1 to the power 4 minus T 2 to the power 4, and what I have here is 1 by epsilon 1 minus 1 plus 1 by epsilon 2 minus 1. So, therefore, the denominator becomes 1 by epsilon 1 plus 1 by epsilon 2 minus 1, these many watts. That is the heat transfer, the total amount of heat transfer, radiative heat exchange between 1 and 2, but in absence of a shield. Now, let us say we have a shield in between these two now. So, I'll draw this circuit diagram over here. So, for this one it is going to be EB1, this one is going to be J1, and the resistance here is 1 minus epsilon 1 by A epsilon 1. So, I take the A to be the same. Then between J1 and J31, so this is J3 facing 1, this should be 1 by AF13, this is the resistance. Then we have between J3 and EB3, so this is EB3, and this resistance obviously is going to be 1 minus epsilon 3 facing 1 by A1 A epsilon 3 facing 1, epsilon 3 facing 1, this is the one. And then from EB3 I will have another resistance for J32, which is just over here. So, this is J31, this is J32, and what is J3? The resistance that connects EB3 and J32 must be equal to 1 minus epsilon 32, unlike this case A epsilon 32. Now, J32 is going to be over here, and this is J2, and this is simply going to be 1 by A F32. So, F13, and this is 1 by A32, and this J2 is connected to EB2, where the resistance in this case would be 1 minus epsilon 2 by A epsilon 2. So, what you see here is, once again, you start at this point, which is EB1. Over here this is J1, J1 to J31, that is the radiosity of surface 3 facing 1. Then you have, for this one you have E3, EB3, EB3 and J32, it is the radiosity of surface 3 facing 2, then J32, and you have to find out what is J2, and J2 and inside it is EB2. So, the number of nodes that you have are 1, 2, 3, 4, 5, 6. So, what you have then is 1, 2, 3, 4, 5, 6. Why we have an extra? Let us see. 1, 2, EB1 to J1, 3, J31, EB3 is this one. So, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6 and 7 nodes. And each of these nodes, between EB1 and J1, you have the surface resistance to radiation. Between J1 and J31, you have the resistance formula for the enclosure, J31 and EB3 surface resistance, and so on. So, you get the complete picture for this. Now, if I write the same Q, the same formula like this one for this, for radiation shields, the formula would simply be Q1 is A sigma T1 to the power 4 minus T2 to the power 4 and the sum of all resistances. So, here we know, where we assume that F13, since the plates are long and parallel, they are going to be equal to 1. Everything is in series. So, the resistances. So, this is the first resistance. Since F13 is equal to 1 and I have taken A to the denominator. So, this is going to be 1 plus 1 minus epsilon 3 1 once again this would be there, this will have a value equal to 1, this is going to be there, this will be there, this value is going to be equal to 1 and this is going to be present in the final expression. So, I have the first one, then 1, the third one, the fourth one, then 1 and then the last one. So, your aim through the use of this shield is to reduce the amount of heat that one is going to lose or one is going to gain, depending on what application you have in mind. So, when you are choosing the material of construction for the radiation shield, the only value that you have to consider is the emissivity. Okay. So, if you look at the expression once again, then you would be able to find out, you would be able to tell like what is the property that you want. So, let us take a look at the expression once again. Your epsilon 1 and epsilon 2 are known to you. So, definitely you would like to use a material of low emissivity for a shield. So, this is what you would prefer. It becomes even more apparent if you simply write this Q 1 as if you take this as 1 by epsilon 1, then this 1 by epsilon 2 is this and minus 1 So, just a bit of reorganization would give you that the heat flow is going to be this and this. Compare that with what we have obtained for the case of Q12 when we did not have any shield. So, because of the presence of the shield, we have an extra term in the denominator, an additional resistance provided by the shield, and looking at the expression you can clearly see you would like to have as small a value of emissivity as possible for the shield material such that this resistance becomes significant. So, this justifies our previous statement that we would like to have for the shield a material of very low epsilon. So, we want low values of epsilon 3.1 and epsilon 3.2 to make our shield, and this part, this term, if you compare it with this one, this term provides the additional resistance due to the presence of the shield material. So, for this special case, and we can make a special case when if epsilon for all the surfaces are equal, then Q1 would be equals A sigma T1 to the power 4 minus T2 to the power 4 2 of 2 by epsilon minus 1. Okay. So, if there are n parallel shells, then this one can be generalized as Q for n number of parallel shells is A sigma T1 to the power 4 minus T2 to the power 4, and this is going to be n plus 1 2 by epsilon minus 1. So, if epsilon is same, that is a special case, you get this expression where it's this part is simply going to be 2 by epsilon minus 1, and here you are simply going to get 2, and therefore, the Q n, in the case of n shells, the formula is going to be this, where this is n plus 1 and this is 2 by epsilon minus 1. So, this is more or less what I wanted to cover in radiation shells. In your text, you would see that if the radiation shells are also common for tubes as well. So, you have a tube which you would like to protect. So, you put another shield over here, and the same concept would also be applicable. That is, the radiation shield is going to provide an additional resistance to radiation for the case of shield. But there you just have to keep in mind that since the geometry is a cylindrical one, so your two areas, the area of the tube side and area of the protection radiation shield, may not be equal, and while writing the resistance, you have to use 1 by A tube F12 in one case, and in the other case, instead of A tube, you have to write A shield. So, if these are very close to each other, you can make an approximation that A shield is equal to A tube, and you will get back to the same result that we have obtained just now. Otherwise, just draw the circuit diagram. In all these cases, draw the circuit diagram, identify what is epsilon 1, what is A1, if are they equal or not, epsilon 1, epsilon 2, etc. Write the resistance to heat transfer in an enclosure, and also write the resistance for heat transfer, the surface resistance to irradiation, what is 1 minus epsilon 1 by A1 epsilon 1. So, and see whether they are connected in parallel or they are connected in series. Are those shells, in the case of shells, they are going to be connected in series one after the other, and you simply have to add the resistances in order to find out what is the total flow of heat in presence or absence of one or a number of shells. So, what I would do is I will give you one more problem to practice on for the case of radiative heat exchange in an enclosure, discuss some of the salient features, and the rest you are going to solve that problem. So, for this problem, what we do is we have chosen a cylindrical furnace. So, this is a cylindrical furnace in which let us call this as my surface 1. So, its area is A1, temperature is T1, and it is a black body. So, epsilon 1 is equal to 1. So, it is a black body. For the case the surface 2 is A2 and its temperature is T2, and this is also a black body. So, epsilon 2 is equal to 1. The surface A3 is insulated. Okay. The length, so this is a cylindrical furnace. The length is 0.3 meter and diameter is also 0.3 meter. So, this is 0.3 and this diameter is also 0.3 meter. Okay. The surface A1 and A2, the end surface and the lateral surface are black, as you can see the way I have drawn it. Epsilon 1 and epsilon 2 are both equal to 1 since they are black bodies, and they are insulated as well. Okay. The temperature of 1 is maintained is at 500 Kelvin, temperature at 2 is 400 Kelvin. I'll change this. A3 is insulated as I have drawn over here. So, let me state the problem once again. It is a cylindrical furnace whose length and diameter are equal. So, this is 0.3 meter, this is also 0.3 meter. The surface 1 and the lateral surface 2 are both black. A1 is to be maintained at 500 Kelvin, A2 has to be maintained at 400 Kelvin. The last surface A3 is insulated. Okay. You have to find the net radiation heat transfer, from each of the surfaces. And find the temperature of A3, that is, you have to find what is the value of T3. It has been given that for such a system F13 is equal to 0.172. So, F1 to 3 is 0.172. The first thing that you have to do is you have to find out the unknown view factors. So, F13 is 0.172. So, F13 plus F11 plus F12 is equal to 1. Since it is a plane surface, F11 is equal to 0. So, you get F12 is equal to 0.828. You can also write from reciprocity relation that A1 F12 is A2 F21, and therefore, the unknown A2 F21 is A1 by A2 times F12. A1 is the circular area 0.3 whole square, A1 is the circular area times A2 is pi dl, the lateral area pi dl, pi into 0.3 into 0.3 times by square by 4 times F12 is given as we have calculated this. So, this is equal to 0.207. So, this F1 to 2 is 0.207. So, from symmetry we can write F21 221 equals F223 is equal to 0.207. So, F221 if it is 0.207, F223 should also be equal to 0.207 because of the symmetry of this case. So, this is a if I draw the circuit diagram for this case, okay. Now, EB1 is equal to J1 since they are 1 is a black body. Okay. EB2 is equal to J2. Both 1 and 2 are black bodies. So, therefore, EB1 is equal to J1 and EB2 equals J2 since these two are black bodies. Additionally, EB3 is equal to J3, but for a different reason, not for a black body, since A3 is insulated. Here A3 is mentioned, A3 is insulated. So, for a different reason, AB3 is equal to J3. However, we have some heat which is coming in as Q1, some heat is coming as Q2, and of course, in this case Q3 is 0 since it is insulated. So, the problem is pretty straightforward. now. So, in order to find the net radiative heat transfer from each of these surfaces, let us find Q1. Q1 would be EB1 minus EB2, Q1 is EB1 minus EB2. This is in series with these two. So, taking an analogy from electrical circuits, it is going to be 1 by A1 F12 plus 1 over 1 by A1 F13 plus 1 by A2 F23, the whole to the power minus 1. So, when you put the values to be this is equal to sigma t to the power 4 and this is sigma t1 to the power 4, sigma t to the power 4, and when you put all the values in there, you are going to should get Q1 to be equal to 143.46 watt. So, that is what Q3 is. The next one is temperature of A3, or in other words, what is the temperature T3 in this case. In all such cases, you need to find out what is J3, and since J3 is equal to EB3, I need to know what is the numerical value of EB3, because the moment I know the value of numerical value of EB3, EB3 is simply equal to sigma T3 to the power 4. Okay. So, I should be able to find out what is T3. So, the step, the trick, the requirement for this specific type of problem is to find out what is J3. And in order to obtain J3, what I am going to say is that to find J3, the flow of heat J3 from J3 to J1 by 1 by A1 F13 must be equal plus J3 minus J2 by 1 by A2 F23 should be equal to 0. That means, the algebraic sum of the current, or in this case the heat at any node is equal to 0. So, J3 minus J1 by the resistance and J3 minus J2 divided by the resistance must be 0 at steady state. So, if you do this, when you put all these values in here, you should be able to see J3 to be equal to 1811.4 watt per meter square. This is equal to EB3 and EB3 is equal to sigma T3 to the power 4. When you put the values in there, you should get the value of T3 to be 422.7 Kelvin. So, this is another example of how you convert the complex radiation exchange geometry to something which now you have the analogy from electrical science, and find out what is the surface resistance to radiation, what is the radiation exchange between the enclosure, and then see which resistance is in parallel, which resistance is in series, and the flow of heat is simply going to be the potential difference based on the blackbody emissive potential divided by the effective resistance between those two surfaces, and everything else follows from there. And in some cases, you have to use the view factor algebra, the relations of the view factor, and you also have to remember that for re-radiating surfaces, the blackbody emissive power is equal to the radiosity for that surface. So, if you keep all this in mind, then the problems on these can be tackled without much of a problem. So, we have one more class left, and in that class I am going to mostly talk about what happens if the system, the enclosure that we are talking about, is filled with a participating medium, which is a very common occurrence where the gases present in the enclosure would start to participate in the radiation process. It would start to absorb some of the radiation, and therefore, it is going to violate one of the major assumptions of the network method, that the gases are not participating in the radiative exchange process. So, that would conclude our study on radiation as well as our this course on heat transfer.